Hello everyone, my name is Neha Kardam and this is lecture 24 on Introduction to Automation. In this lecture, we'll continue our discussion about AC motors. We'll be particularly looking at the AC motor control. So, when an AC motor is initially switched on, there is often a surge in current. Sometimes it is as high as 5 times the average running current. While this surge is usually manageable for fractional HP motors or horsepower motors, special measures are required for large motors to prevent the strain on electrical and the mechanical components. And the common method to start a fractional horsepower AC motor is by directly connecting it to the line voltage through a switch. So as you can see in this circuit diagram, it is directly connected to the line voltage through the switch. And this approach, as shown in the circuit and also illustrated in the ladder diagram, typically is a representation in industrial motor winding diagrams. And in ladder diagram, we have L1 and L2. They basically represents the AC line voltage wires, and each rung, this is called the each rung, symbolized a circuit. An overload device is integrated into the circuit to open its contacts if the motor is overheats, providing an additional layer of protection. For industrial processes, motor control system, they are often more sophisticated than a simple toggle switch that you see over here. And motor may be controlled from a remote control panel or using the relays. And these relays which are used to control the motor, they are basically magnetic motor starters or contactors which are designed to handle motor current and also include built-in current overload protection. And if the current exceeds a preset value, then what will happen? The contacts of the starter open, and in that situation it will safeguard the motor. So using the basic toggle switch for motor can basically pose the safety risk. So for instance, if a motor overheats and the overload protection shuts it down, then someone may assume it's safe to investigate. However, if the thermal protection resets while the power switch remains on, the motor could suddenly restart, and potentially it can cause harm to the unsuspecting individual or the person who is operating that. So this is how the motor control can work, and just an example, simple example of that. Now moving on, now in this we will examine a start-stop circuit for single-phase AC motor. So in this circuit, we have the stop and start button, and the stop button is normally closed while the start button is normally open. So this is a symbol for the normally open switch. When the start button is pressed, power is supplied to the motor starter relay coil. This is the motor starter relay coil M, and it will close the contact M1, and also it will close the contact M2. So M2 connects to the motor. This is the motor. M2 connects to the motor to the AC power, and it initiating the basically it's connected to the motor power, and it initiate the motor operation. Now meanwhile we have M1 which connects to the relay coil to a point ahead of the start button, as you can see over here. And it allows the relay to remain energized even after the start button is released. And this process known as sealing or latching, and it maintains the relay's energized state. Now, upon pressing the stop button, the power to the relay coil is cut off, and it will open up the contact M1 and M2. So M2, when M2 is opened, then it will stop the motor, while M1 opening releases the seal of the relay coil, and it ensures that the motor remains off even after the stop button is released. Now, in case of a overload, the motor will stop as if the stop button is pressed, and it will not restart until the start button is pressed again. Now here is the ladder diagram of this. So a ladder diagram of this start-stop circuit is shown. This is the stop button, this is the start button, and this is M1 contact. This is the relay coil, the same thing here. And here is the motor, and this is the M2 contact. So now, apart from a safety consideration, the sealing circuit are very beneficial for managing the power restoration scenarios. Instead of all motors starting simultaneously after a power outage, causing a surge in the current, motors can be restarted individually or in they can be started in a group in an orderly manner. Also, starting and stopping motors from multiple locations is common practice, and it also ensures the flexibility and control in various industrial settings. So this was about start-stop circuit in a single-phase AC motor. Now is the start-stop circuit with a provision of jogging. So here we introduce the concept of jogging. So in this circuit that you see over here, jogging basically refers, this is the jog. Jogging refers to applying power to the motor in short bursts for tasks like inching a device into a desired position or making minor adjustments. So for instance, commercial mixers might need to be jogged to facilitate the blade replacement. For example, in your home appliances, the mixer that you use or the blender that you use, it may have the jog to facilitate the blade replacement or motor driving. The last shafts it might require the jogging to align the keyways with mating parts. So switch A, so in the switch A that you see allows for two operating modes. The first is to start and jog, the start and the jog. So in the start mode, the circuit functions similarly to the standard start-stop circuit with the relay being sealed every time the start button is pressed. However, when the jog mode is pressed, the sealing circuit is disabled. So in that case, the sealing circuit is disabled and the power is supplied to the motor only when the start button is pressed. Now, jogging is commonly used in the applications such as motion control, machine tooling, and I already mentioned that it is being used in the mixture. And it is used where we want precise adjustment and positioning, where the positioning is important. Now, it is important to note that the jogging should be used judiciously, as frequent jogging can also lead to a heat generation. So if there is a frequent jogging, then it can cause more heat, and potentially it will reduce the lifespan of the motor and the contactors. So as a general guideline, what we do is this jogging should not be performed more than 5 times in a minute to mitigate any heat related issue. Now let's delve into the concept of reduced voltage starting, and this is one of the simplest methods to limit startup current by using resistors in series with the motor during the startup phase. And after reaching a certain speed and drawing a reduced current, a switching mechanism removes the resistors from the circuit and connecting the motors to the full line voltage. So the resistors that I'm talking about, these are the resistors which are illustrated in the circuit. So So in this you will notice that R1, R2 and R3 in series with the motor power lines, and each resistor is bypassed with a relay contacts. When the start button is pressed, the MR relay coils, this MR relay coils that you see, MR1, 2 and 3, they are energized, and closing the contacts of these three and connecting to the motor to the power line via the resistors. Another MR contacts, which is MR5 and MR4, these are they powers the coil by a timer relay, which delays its contacts from closing until the motor is near to the operating speed. And once the timer relay times out, this timer relay is times out, the contact TR1 closes, and when it is closes, it's allow the relay coil. It allows the relay coil RB, this relay coil, to energize. Now this relay RB equipped with the contacts RB1 and RB3. So this is RB1 and RB3, which connects the motor and directly to the power lines, bypassing the resistors. Now this reduced voltage starting circuit is very cost effective. It does come with some drawbacks. Reduced motor startup torque is produced in this, and the torque, that is the reduced startup torque which is produced, is directly proportional to the current, and limiting the current. Consequently, it limits the torque. Now to mitigate this, we can use the transformers instead of the resistors that you see here. And transformers, they offer the advantage of providing increased current to the motor without starting the power distribution system. And these transformers, the transformer which are used, if we can use that, they also engage during the startup, and once the motor reaches operational speed, they are switched out, allowing the motor to be powered directly from the power lines. Now moving on to the next, here we are going to explore the variable speed control of the AC motors. Now, achieving a variable speed control for AC motor can be possible through off-the-shelf power conversion, which is capable of converting the standard line voltage at 60 Hertz into a wide range of voltages and frequencies. A motor control units, or the combination of the control unit and the motor itself, is commonly referred to as a drive. And there are four main options for AC motor variable speed drives. First one is variable frequency drive, second is the vector drive, third is the flux vector control, and the field oriented control. So in the variable frequency drive, this is one of the oldest method where the frequency and the voltage supplied to the motor are varied simultaneously in proportion to the control the speed. And in the vector drive, or it is in a vector drive, this method, it estimates the motor speed and rotor flux using the mathematical models, which allows for precise control of speed and torque without the need for any additional sensors. And this flux vector control, it directly measures the motor flux, which enables accurate control of both speed and the torque. And finally, this field-oriented control, which is also known as vector control, and this method individually controls the flux and the torque components of the motor current, offering precise control over the speed and the torque. And these variable speed drives, they offer flexibility and efficiency in controlling the speed of the AC motor across a wide range of applications. So here is an example is given where 60 Hertz AC is given to it, frequency is given to it, which converts AC into DC to any DC voltage, and DC to AC converter is here to any frequency, and which is given to the AC motor. Now this is the frequency variable frequency drive circuit, uh, which is the variable speed control of AC motor, one of the method. And in this circuit, we convert the 60 Hertz AC power into the DC using a silicon control rectifier. They are also called in short form as SCR. And these SCRs are used to control the magnitude of the DC voltage. Remember that an AC SCR conducts when two conditions are met. The first is they should be forward biased, and it receives a trigger pulse on its gate input. This is the gated input, and it should be positive biased, and it should receive a pulse at the gate input. So in this figure, if the gate G that you see of each SCR is pulsed at the beginning of each positive AC cycle, then the SCR starts conducts for the maximum duration, and also resulting in the maximum DC voltage. Conversely, delaying the trigger pulse reduces the SCR's conduction time, and it can lead to lower DC voltage if the triggering is done is delayed. And the inductor and the capacitor component that you see in the circuit, they are used to help smooth out the power pulses from the SCRs, and that is why they are used. And to control the average value of the DC voltage, we adjust the delay of the trigger pulse, which I mentioned it before, and the circuit generates the three-phase AC power at any desired frequency using this 6 transistor that you see here on the right hand side. So a control circuit, the sequence of turning these transistors on and off, creating the sine waves. It will create the sine waves, and this creates the versatile circuit that offers the precise control over the DC voltage, magnitude, and the frequency of the three-phase AC power. So as you can see, here is the AC voltage, and the filtered out DC voltage is here obtained and sent to the motor. Now let's examine the output voltage waveform of the speed control circuit that we saw earlier. So it has there are 3 types that we see here. The first is the pseudo 3-phase simple waveform, and in this configuration we generate a pseudo 3-wave waveform using the basic switching mechanism. The output waveform resembles a 3-phase AC signal, but it's generated using a simple control technique. The second one is using the pulse width modulation, and in this technique, to create a pseudo 3-phase waveform, we use pulse width modulation, which allows for finer control. As you can see, these are the finer control over the output signal by adjusting the width of the pulses, which results in smoother and more precise waveforms compared to the simple method that you see here. Now the actual 3-phase waveform represents the ideal output for the 3-phase system, and this waveform is generated using the genuine 3-phase power sources, and it provides the most accurate representation of the true 3-phase AC power. Now by comparing these waveforms, we can observe the difference in the complexity, accuracy, and controllability among the various methods of generating the 3-phase like signals. So this was about the output voltage waveforms of a speed control circuit, and that's the end of the lecture. Thank you so much for listening to me.